3D prints are weak.
But they don't have to be. There are all kinds of different solutions for making your prints a lot stronger than they have to be. So inside of this video, we're going to show you more than 20 different ways to make your 3D prints stronger, whether you're bending them this way, this way, this way, or just putting them in any orientation that you happen to feel like. So enjoy this group of solutions for making your 3D prints stronger.
So you want to 3D print a vertical rod, but you don't want it to split in half. Today in this video, we're going to talk about how to prevent that, not through slicer settings, but through actual design. Now this is a real common problem. People don't want their 3D printed parts to just break in half whenever you push along them. But how do you make them tougher? 3D printed parts break along the layer lines. No, they don't. 3D printed parts admittedly are weaker for the material because of the printed layer lines, but that just means you design around them. If you're gonna make an airplane out of wood, you're gonna design it a little bit differently than if you make it out of aluminum or cloth. There are different rules. So with 3D printing, if you wanna make a part a little bit stronger, what a lot of people do is they go into the slicer settings and they make the walls thicker. That's actually correct. For cantilevered beam, thicker walls are actually good because they put the material out where the actual compression and flexure is inside of the beam. As it bends, the top spreads and the bottom compresses. So having thicker walls puts more material up there where it matters. But the issue is now you're dependent on slicer settings. If you upload that file to a manufacturer to have produced, you're now transferring files and then they don't translate to the machine and everything just goes to heck. It's terrible. So what you want to do is you want to actually design your 3D model so that it has wall thickness where you need it. But you're going to say, hey Gabe, if you design a rod, well, you're not going to be able to control the wall thickness. Incorrect. You actually can control the wall thickness. And here's how I'm going to tell you. It's a little bit of a hack. What you do is you can actually embed a pattern, basically a bunch of holes around the outer part of the part. For example, with this rod, I just put a bunch of circles around the outer edge and cut holes through it. What I have now just done is thicken the walls of the entire part, because now there is more material around the outer edges because you're filling in the walls rather than simply having infill go out to the outer skin and then coming back. This is a way more reliable way to produce more material. Now, even though you can just design holes and put them around the outer edge, there's a few different ways that you want to go about it. We're going to post a video over on the Tangled Testing channel about the design of these different holes that will go into more detail about what the right way to do it is, because some are good, some are very bad. Now, the designs that we went through in this video are outer ripples, holes around the outer edge, kind of an arrow pattern around the outer edge, and what we call ribs, which are just slots along the outer edge. All of these induce the slicer to create more material out in the outer edges. But the trick with all of these is that they're exceptionally thin. Each one of these features is basically 0.2 millimeters wide. And the reason for this is that is large enough for most slicers to identify it, but small enough to where when they print along it, the walls basically fuse together. Because the last thing you want are the walls to be spread out, because if you do a ripple around the outer side and it prints spread apart as two separate walls, then all you did was create a sleeve around a center core, which actually makes it weaker. So you make these features very, very small so that they just make more material go there, but they don't actually split the part across or create any sort of stress concentrations. Of the ones that we used, the ribs was actually the best. When we ran our test with a simple cylinder that just had a simple infill and a simple 1 millimeter wall, it was almost a third as strong as the ribbed design that we did. If you uploaded it to our API, the ribbed version would use more material and be a little bit more expensive, but it would be so much stronger, and you would not be reliant on the slicer settings to create that more strength. You wouldn't have to say, oh, I need the wall thickness to be 4 millimeters or something like that. You simply design in very thin features that are 4 millimeters thick, and they induce that wall. Now, if you get fancier with this geometry, what you're doing is you're now creating a 3D printed rod inside of a 3D printed part. So you are able to build up strength across the part without having to add additional features or worry about the homogeneity of it. Now, of course, the easiest answer to all of this is just do a solid infill part. But barring that, when you want lightweighting but controlled strength in particular areas, what you can do is you can introduce these microstructures, which then cause the slicer to put more material where you want it inside of a part, so that when you want to print a part, it doesn't break anymore. This is a specific but oddly common type of part that we have to make inside of our print farms. So today we're going to talk about how to optimize a ring with some clamps on top of it. So this design comes up a lot. There's a lot of these types of pipe fittings out there that are meant to connect two things together, catch stuff, or whatever it happens to be. And it comes up in a lot of different formats too, so like lids of enclosures and that kind of thing, where you have these clamps on top of something else. Now, whenever somebody tries to print this, they put it down on the bed just like that, but now the layer lines are in the plane of the clips. So as soon as you start reefing on it, those snap right off. You can use different materials in order to optimize this, but really it's about the design. So we're going to show you some really nifty designs to get around this. However, if you're stuck with this, if it has to be printed like this, there's a few things that you can do. First of all, like I say, you can change the material. You don't print it in PLA, you print it in something like PETG or nylon or something else, so you get a little bit better layer adhesion. On our side, we're able to experiment more and make those stick a whole lot better if we're allowed to kind of over extrude and if tolerances are really low. So there's a way to get it printed like that to where there's really good layer adhesion, but then the surface finish might get messed up. The other thing you can do is make just minor modifications to the design. If you want to print it like this, that's fine, but then the point of failure again is those clips. If you want to reinforce those, you can just add some chamfers to the outer edges of them so that now they are actually reinforced and able to stay there. In that way, you're losing some flexibility and you have to rely on the flexibility of the ring rather than flexibility of the clips, so it's not always a good option. With the design of this though too, just in general, make sure that you're filleting the lower edge that's in contact with the bed. That way we don't have to worry about elephant footing or other sort of first layer artifacts. It just preps it for the piece if you're stuck with this. But let's go ahead and move on to something a little bit better. The very first and easiest solution is to just print it at an angle like this, not on its side, at an angle. What this does is it now puts the layer lines partially in plane with the clips without requiring support on the clips so that you can actually grow this part up and easily. All of the clips get way stronger because again, the layer lines are almost in plane with them, and it becomes much easier to mass produce. However, sometimes you do require a brim down on the bottom to adhere it to the bed and potentially even some support underneath here. The other issue that can come up is a lot of roughness and nastiness on these back edges that are an overhang because it's a fairly steep overhang and a fairly thin, fragile part. So in order to reduce this, again, fillet it, round out the edges. Sharp edges that are overhangs always warp and deform, so avoid them as much as possible. But that also requires a small cut on the bottom so that you actually have a flat surface to put against the bed. If you don't have a flat surface, then the part is going to fail all the time and you're going to radically increase your costs. Now, of course, you can also extend this out to the traditional piece itself. Taking the same chamfered piece makes it even better because now you don't have to worry about the overhangs of the clips themselves, and you're again able to balance it up right here on its edge just as it's sitting there. Now, going a little bit further than that, with those fillets and those chamfers, when you're printing on its edge like this, you have effectively eliminated the overhangs. And you can take this a little bit further by adding an octagonal outer pattern. This is only necessary if the strength of the clips are absolutely critical and you need to maximize that. In this situation, you want to print it on its side. Printing it on its side allows all of the layer lines to be in plane with the clips. In this case, you also want to make sure that the clips themselves are at a 45-degree angle to horizontal, because if you have one on top and one on the bottom, now they're again in a plane where they can break off because the layers can delaminate. Putting them on the diagonal side makes sure that they're not able to do that. So you're printing it on its side like this. Now you're running into a different issue that you have to be aware of, in that there's this effectively overhang inside of here. The best way to deal with that is with designed interior support rather than auto-generated support that we might provide if we were prepping the parts for you. If that's done incorrectly, you can end up with a lot of this kind of nastiness on the top, where you have this sagging and weird sort of delamination of the layers, and it just doesn't look very good. You also have to be aware of the tongues, that if they overhang in any way in one direction, which these do because they have kind of an L shape where they go up and then out. So in order to achieve that, you're gonna have an overhang that's just unsupported, and you have support underneath there. You can tweak this a little bit by taking these tongues and moving them closer together so that these two bottom ones interface with the bed and they lay straight against the bed. That way you don't have to deal with supporting underneath them. And then these upper ones also grow into themselves from this chamfer down here. So hopefully that shows you how to make a very simple ring with some clips on it, or how to make any sort of shape that needs these clips. Being able to print on its side reinforces these a great deal so that you don't have to worry about them breaking off. And there's a lot of other geometrical changes that you can make in order to make sure that this part is as reliable as if it was made with injection molding. But now you don't have the cost of tooling, you have the scale and flexibility of 3D printing farms, and you're able to change the design anytime you need it. Almost everybody ends up doing this wrong. So today we're going to talk about how to design side loops on 3D printed parts. Now the challenge with side loops is that very often they're just a brittle part. They're a component that can can be pulled out very easily because you have layers that do not have a lot of support around the outer side, and you're not able to make them very thick in order to get what you want out of them. A lot of people end up designing kind of these wiry sort of side loops, which again, just don't have a lot of material. If somebody puts a lot of force on that, they're gonna snap off. Heck, if they get dropped, they could potentially snap off depending on what your material is. Now, while these can be reinforced by picking good materials, it's better to just do the CAD correctly in order to create something that is reliable. So the very first and simplest way of doing this is actually not to do like a full loop, but just have a hole in a plate basically on the side. You can make it elliptical or perfectly round. Make the side loop plate as large as you possibly can to give it as much meat as you possibly can, and then just to punch a hole right through. That could be for your zip tie, for your cord, whatever it happens to be. This is a good, simple way of modeling it up and gives you the material that you need to make sure that this thing is reliable. But there is still the potential for pullout. So if we wanted to reinforce that a little bit more, you can take it kind of a step further. And the way I like to do this is actually to put a rib on the outside of the plate. This way, this rib can act as a reinforcing actor. It can go all the way from the base of the side loop to the very top, or you can actually design it to be kind of like a little T flange on the outer edge, where it's just adding material right at that pull-out stress concentration without having any issues. Throughout all of this, of course, make sure there are no vertical overhangs so you don't have support. Make sure everything is angled so that every part can grow on the part previous to it. And then just make sure you fillet everything. Please make sure you fillet everything. And of course, the very simplest solution of fixing all of this is to just make these side planes really, really thick and fat. You can have them loop the entire part or whatever it happens to be in order to make sure that they're reinforced and strong. But ultimately what you're trying to do is you're trying to add more material, more reinforcement around the pull-out area in order to make sure that it's strong and reliable. Do not just leave a simple plane of vertical layers on the outside that's going to be thin and is going to be delicate. This way you can make a part that's really robust, can last as long as you need it to, and can actually replace a traditionally manufactured part very reliably without any issues. Because these features that we just discussed are not typical inside of normal design. A lot of these could not be molded or produced with traditional sort of methodologies, but 3D printing enables them now, and it also necessitates them in order to have a reliable part. So if you want to mass produce a part in quantities of thousands like what we do here at Slant 3D, make sure you're using these reinforcement strategies.
A lot of people want to mount parts to the walls, 3D printed parts to the walls. You might want to run screws into them, you might want to put up a handle, you might want to just mount up an electrical enclosure or something. And people will always print a part in this orientation with the layers going up, screw it into the wall, and then very promptly have the layer lines break out and split along the holes. So what are ways of getting rid of that? Well, it's important to understand the mechanism that's happening here. You're dealing with the layer adhesion of the part. Can those layer lines stay stuck together strong enough in order to not split when put under pressure? This is based on the adhesion of the material itself, but also the surface contact area. Now, this is a design video, so we're going to talk about surface contact area. If you have more contact between the layers, you will have stronger layers. So let's go ahead and look at the very first version of that. The simplest way of doing this is actually to just put threads in the holes, which seems counterintuitive because they can introduce stress concentrations, but what you are also doing is increasing the length of the layers right next to the hole where the pressure is, so there's more surface contact area around the hole. Threads are basically a way to thicken the walls around the hole so that now you have more material around the hole where a crack can start. That's a very simple way to model it, but it's not the best way because, like I say, all of those are points inside of the hole, and when you have a point right up against some piece of force, it can cause a crack that then propagates through the rest of it. So what are some other ways of getting this done? Well, you can thicken, you just don't have to thicken the entire thing. You can extrude the area around the hole and either deepen the area around the hole so that that hole is supported by material just locally around it, which can be very helpful because now you have more contact area, but you've also increased the space for infill, so it can be a little bit of a double-edged sword. A way of fixing this is to, instead of simply having an offset, is to just put rings around the hole. And now you're wrinkling the front surface to where if any crack formed, it would have to go through all of that space before it gets to the main meat of the part holding it up. And those rings are very simple to model. They are still just the simple offset, but with a few more indents into them. But ultimately what they can do is just create some structure around the hole so there's just more material there holding the hole together. And this can be incredibly useful. There's a few other ways of doing this. You don't necessarily have to use circles. Everything splits in just this direction. So you can create kind of linear solutions to it, where you have just struts right alongside that are very localized area of thickness so that it has to split through this whole big old thick area of material before splitting into the rest of the part. And again, this can be easier to model and can be useful in particular sort of use cases. But all of those are external features. Sometimes you still need the thing to be flat and you just want it to be solid in that area. Now, most people would say you would use a slicer for this, but a slicer is a wrong sort of tool for this because you should be able to create a model for an object and then send it to machinery and have any piece of machinery make that model to spec without having to worry about settings or materials or the rotation of the earth, which is what you do when you start messing with slicer settings, because one slicer will slice differently from another, one machine will print differently from another, one material will print differently than another. So if you're using slicer settings, they're very fragile, but if you design these types of features into your parts, they can work anywhere, anytime, at any scale, always. So what I would like to do is model into the part ways to make sure that it is solid around the hole. And the way you do that, you cut up the part. This is gonna sound counterintuitive, but what you can do is around the hole, basically just put a disc and you cut it so that it's like a 0.1 to 0.2 millimeter thick cut. And what it does is it just induces any slicer to create walls around that area, which are not viewed from the outside. So if you have a 1 millimeter thick wall and a 2 millimeter thick part and you create a small cut between the middle of it, you just created a solid part. So what I like to do is put these discs around holes, and now you're able to create a fully solid area around that part. It's not a lot of extra modeling. It's a lot stronger and it's a lot more controllable because it will work on any machine or material without having to redo all your slicer settings. And if you want to do this over a thicker part and that kind of stuff, you can just repeat that pattern over and over again and you create these solid rings around your hole. You do want them to be vertical because you want the layers to go along it. You don't really want to do holes all the way around or those types of micro features, which you might use in other scenarios. For these, you just want a small cut, little slats inside of your part, and it creates something that can be really, really strong because you are creating a lot more surface area, basically a solid printed part that is pressed together. And you're able to use any slicer anytime, anywhere, and no one ever sees that you did it. So now, instead of giving people a big old recipe of how to make the part, you can just hand over the part and that part will be made perfectly every time. And this is why it's so important to create it, because if you want to mass produce these parts or send them to a manufacturer, you want it to be made the way you anticipate. And slicer settings don't do that. So for using portals where you can just upload a model and start selling in like 30 seconds, it's really important to just upload a model and get what you want and get it selling in 30 seconds without needing modifiers or your particular material or your particular brand. If you model it in specifically into the part will always be what you want and you don't have to worry about any of the other details. This makes a part that is really easy to manufacture, really robust, and is way more affordable too because there's a lot less work to keep it straight. So hopefully this has been a good demonstration of how to design side mount holes that are actually sort of strong rather than just 3D printed layer splitting problems. You don't want to perforate your 3D printed part, you want to reinforce your printed part. And these are a number of different ways of reinforcing those types of holes.
When designing a handle for mass production 3D printing in a large print farm like this, there's a lot of things that you want to consider in order to make sure that it's designed correctly. So in this video, we're going to go through how to design a handle so that it can be mass produced and how to make sure that it's actually strong enough to do whatever it is that you need it to do.
So handles are a very simple sort of device. They've been around forever, and one of the simplest handles that you can make is the one that you might find all over your kitchen or house, which is a simple crossbar with 2 screws at either end. These are very reliable handles that are very ergonomic and have a lot of artistic expression within them. As you look around your house, you'll probably see them all over. But all of these handles historically have been designed to be made with stamping of metal or carving out of wood because that's where they were originally designed to be made. But we have new technologies available, things like mass production 3D printing. But if you're going to mass produce a product, you cannot design it for some old style of manufacturing. You have to understand the end process that you're going to use. So you can't just simply do a standard handle where you would then round off the edges and drill a hole in it. It's not a piece of bent steel. It has different structural needs, so you have to design around those. Now, one of the simplest solutions to this is to simply use what we always love to use, which are chamfers, and basically create ribs around where the holes are. These ribs don't really require much support material, and they can be easily mass produced, and they leave lots of room for the hole and for the screw head itself. And this is a perfectly reasonable way to do it. And then you could go around and you could fillet the edges so that it has a nice smooth feel to the touch and it doesn't have any sharp edges. And that's pretty much all you need to do. There's no controlled stress concentrations or anything else. This handle is perfectly decent and could be used for furniture or industrial equipment or anything else along those lines. And you could follow this principle, but it doesn't look very good and it looks kind of amateurish. There's a next step that you can take this to where you actually use the chamfers and you lean into them completely. Again, this handle is printed on its side, so we have all the layer lines in the right direction, so it has maximum strength there. But again, we're making sure that the holes don't pull out. So why have ribs when you can fill in all the area around it? There's no worry about shrinkage of material or warping or anything along those lines. Use all of the enclosed volume that you can because you can add more material there in order to reinforce the part. Now you're also getting rid of those large cavities that were left by the ribs. Ribs are really sort of a last century solution when they were limited by what traditional tooling could produce, but 3D printing does not have those limitations. So use that space, use that material, use that volume of the part. Now you can just have a countersunk hole that allows the screw head to enter into it. Now you have a lot of supported material around it that's very deep. You have a very uniform looking part that no longer has cutouts out of it or anything else. And since we like chamfers all the way around, we're going to apply them all of the way around with just a little bit of rounding on the inside to make sure those edges are soft if somebody has some soft hands coming by. But while we're at this, 3D printing allows us to apply textures for basically no cost whatsoever. So we'll also go ahead and put a small grip texture along the inside of it. This makes sure that this has a little bit extra friction, regardless of where its application is or the state of the hands that are using it, making it much better for industrial applications. Now we have a handle that is dimensionally equivalent to any other handle that could have existed, but rather than designing it as if we were bending expensive steel or trying to make it fit into a carved out piece of stone in a mold, we instead have the freedom to create a part that is very uniform and monolithic and strong, while still having the subtleties of texture and fit and finish that you can't really get from any other option. And not only does this handle look really good, especially when we print it out in a nice glossy gold, because we can pick any color that we want, even if we were producing 1 million of them. We could change them up to have 100,000 in red, 100,000 in green, and 10 over in the gold. It's not that hard to do, because again, we're using mass production 3D printing to make this part. This part is now finished, reliable, and can take the full weight of a human hanging upside down from it. It's hard to find many applications where the person will pull on a handle harder than they can possibly hang from the handle. And that's how you design a handle for mass production 3D printing. We love chamfers, and you always want to make sure that you actually design for the process that you're using. If you try to use some old design style and push it into 3D printing, you'll probably be disappointed. But if you use the technology for all the benefits that it can create, you can manage your supply chain, reduce the cost of tooling that you had before, and modify your supply chain so it's much tighter and easier to get the parts when you need them and in the quantity that you need. You have all those advantages, and all you have to do is make some small design modifications to make a better part anyway that truly differentiates you from what any of your competitors would be looking at. So while this was a simple handle, it can be applied to any other number of parts to create something that is truly exceptional and unique. Have a great day, everybody.